I think let's get started. So today, what I have done is that I thought that uh, let's try to save some time because we have a limited time. So I've tried to create a template today, and we'll try to follow this template for our session. So today we are going to start with the queue data structure. Okay. For a queue data structure, basically it's first in, first out. So whoever who comes, the entry which is added the first time into the data structure will be the one which will be removed first. So this is the beauty of a queue data structure. So I've just given a very bad diagram down. For example, you might have, if you go for booking of a movie ticket, or if you go for a ticket reservation in the railway, right? The person who comes first and collect the ticket is the one who gets the first chance, right? So this is the first come first serve thing. So this is what the queue data structure is. So whichever entry that comes first is the one which will be uh, you know will be brought into the action. Okay, can you guys think of any use case where the queue data structure might be used? First come first something in your day to day computers use cases. I think most of you, I think Zahir, you are still in the college, but I think Paritosh, you are already working, right? So can you tell me a few of the examples practically where queue is being used?
Like for example, in games, say for example, if suppose the person is firing in the bullets or something, so we might create a structure of queue.
Okay, okay, makes sense, makes sense. Anywhere else that you see in the application that you have created? Uh, so, for example, if you have created a web application, suppose, okay, so suppose you have a web application like this, web app, okay, and suppose this web app that you have created is having say a QPS of say 100. What is 100 query pen? So QPS is driven by how much the thread pool, right? So normally how many threads are there in your pool, that drives how much QPS your particular server can support, right? Now suppose what happens, there are clients calling your server, okay, and suppose the number of calls that this client is making to your server is say like 200 now, 200 concurrent calls. Okay. So what happens is that now your system is only able to support 100 calls at a time, 100 queries per second. But say number of concurrent call that is happening right now is 200, right? So you need to support this, right? You cannot say the remaining 100 people that go back, I'll not be able to give you the response, right? Because that would be a very bad customer experience. So normally what you do in that case again is that before call of the server, you maintain a queue kind of data structure here. Okay,
Okay,
and the 100 calls you are able to process, and the remaining 100 to queue it here,
okay,
and then as and when your threads get free, you will pick this one, then you'll pick this one, then you'll pick this one, then you'll pick this one. So that is another way, one of the very common and the great use cases of the queue. So whenever you have to scale systems and which there's upper bound to your number of queries that you can do based on the pool size that you have created for your system. But still, if suppose in certain spike situations, the number of requests is more than that, you still maintain a queue where you don't lose your customer. Now, the response time will definitely be hit because they will be serviced later on, but still they will be given some service, right? Will they not be outrightly rejected? Okay, so that is one of the biggest use cases of the queue. Another use case of a queue is that you might would have heard about the messaging systems, right? Messaging systems
yeah.
like Kafka.
Are you aware of the Signal R? Are you aware of that? I mean,
Signal R is an open source or it's a proprietary?
it's a real time messaging thing. Like for example, it is used in chat. Like basically
Okay,
we in C sharp or in .NET profile we use that. And
okay,
for Java and open source, I don't remember, but definitely we use Signal
okay,
R for this. It
okay,
uses the same concept actually for the messaging.
okay, okay. Okay. So basically, yeah, the concept of the messaging system is simply publisher subscriber design pattern,
Yeah,
and
yeah,
there's multiple implementation of it. Most famous among are the Kafka, Active MQ, Rabbit MQ, and even Redis to some extent, and maybe there's so many implementation. Even all the cloud providers have their own messaging system. For example, AWS has their own support for a messaging system. But whatever messaging system is, they all are powered internally because of the queue, because it's the queue which follows the first in first out order. So whatever the messages that were pushed in first is the one which will be taken out, right? So this is the beauty of what queue is. So understanding queue help us to understand these so many systems. Cool.
Okay.
Now coming back to the key terms in the queue, just like in our stack, we have a queue two key terms, which was a push and a pop. Similarly, in the case of the queue, we have a two terms. One is known as the N queue, and we have something called D queue. So N queue means is another term for adding add element, and the D queue is another term for removing the element. Okay, so whenever I have to add anything in a queue, I say that I'm enqueuing it, and if I have to say I have to remove anything, I'll be saying that I'm dequeuing it, right? And just like the stack in which the push and the pop has to be done in a constant time, similarly the queue also, the both enqueue operation and the dequeue operation has to be done in a constant time. So given a queue, you can take it for granted, right? You can take it for granted that its in-queue operation will be also done in the constant time, and its dequeue operation will be also done in a constant time. You don't have to worry about the underlying implementation. But if somebody tells you that okay, you are using a queue, it means that the in-queue operation should happen in a constant time, and the dequeue operations will also happen in a constant time. So the time complexity should be O of one of this one also, and O of one of this also. Okay. And that is how in any of a messaging system, right, here also, right, we are using queue data structure, because whenever we have to add any data or whenever you have to remove any data, it guarantees a constant time. So I get a very good performance advantage also, irrespective of the size of the queue, irrespective of the number of messages in this queue, or the number of messages in the Kafka, or your serial RI or active MQ. So whenever I have to push a data, or whenever I have to enqueue a data, or whenever I have to dequeue a data, uh, the time that it will take will always be constant, right? So that is the beauty of enqueue and dequeue is. Apart from that, few more things that we need to support in a queue data structure, which is like one is empty, which will say whether the queue is empty or not. The second one is full, and enqueue and dequeue we have already seen. Okay. So this is what on a high level a queue data structure is, and now we have understood where it is being all used, what kind of data structure it is, and what is the two key basic characteristic of a queue data structure. It is about enqueuing and dequeuing in a first in first out order in a constant time.